Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akil Iman bin Sharifuddin. My matrix number is DE230112. So we are from Group 4 and we will present about our project through this slide presentation. Next, we move to the group members. First, Muhammad Shakir bin Muhammad Faiza, DE230052. Next, Muhammad Akil Iman bin Sharifuddin, DE230112. Next, Muhammad Mustaqim bin Jamaluddin, DE230098. And next, Muhammad Hanan bin Abdul Samad, AE220121. And last, Muhammad Zul Izwan bin Zulkhairi, DE230104.
We'll start with the importance of tuning controllers. In many practical systems, we don't have a complete mathematical model, which is why empirical methods like Ziegler-Nichols are so valuable. This technique is widely used for tuning P, PI, and PID controllers, and it works both for open-loop and closed-loop systems. In open-loop tuning, we apply a step input and observe the system output to measure a delay time and time constant. These values are then used to estimate controller gains. In contrast, closed-loop tuning involves using a proportional controller and increasing the gain until the system oscillates. At this point, we record the ultimate gain and the ultimate period, which form the basis for calculating the PID parameters. Beyond tuning, understanding the system transfer function is critical for second-order system parameters like the damping ratio and natural frequency. Determine how the system reacts, whether it oscillates or settles quickly. Third-order system with more complex dynamics require a careful analysis due to the presence of additional poles and interaction. Ultimately, these methods and models help us meet key design objectives: stability, responsiveness, steady state accuracy, and also robustness. Now I'll be walking you through the key objective of control system. Let's begin with the stability, arguably the most critical goal. A stable system responds to input or disturbances and eventually settles. Without stability, even the best designed system can spiral into chaotic behavior. Next, we look at the steady state accuracy. This refers to how closely the system's output matches the desired value after the initial response. A control system with high steady state acquired accuracy aims for zero error, especially important in precision tasks like robotics or automation. We then move to the desired damping behavior, which is determined by the damping ratio denoted or zeta. If zeta is less than 1, we get underdamped responses, fast but oscillatory. At zeta equals 1, the system is critically damped, offering the fastest non-oscillatory response. Overdamped system, where zeta is greater than 1, responds slowly but smoothly. And if zeta is equal to 0, the system doesn't settle, it just keeps oscillating. Lastly, we have the transient response quality, which describes how the system behaves immediately after a change. We target four main traits here: a fast rise time, low overshoot, minimal oscillations, and short settling time. Together, these make the system agile and responsive without being unstable. So, whether we are designing a self-driving car or tuning a temperature controller, these objectives give us a solid foundation to build a system that are both intelligent and dependable.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shakir bin Muhammad Faiza, and now I will explain the calculation for the assignment. So first, for the manual calculation is we need to define the DC motor equation. So first we have the electrical equation for the DC motor equation, which is VAT is equal to LA DIA T over dt plus RAIA T plus EB T, which is VA is the armature voltage, IA is the armature current, and EB is equal to KB omega M, which is the back EMF. And then we need to define the mechanical equation. So for the mechanical equation, the equation is Tm is equal to JEQ times with d omega m over dt plus BEQ omega m, which Tm is the motor torque, omega m is the angular speed of the motor, JEQ is equal to Jm plus JL, and BEQ is equal to Bm plus DL. So by having this both of this equation, we can combine them to produce to produce omega ls over va. S is equal to ka over bracket las plus ra times with bracket jeqs plus beq time plus with ka kb. Once we combine this both into be a single transfer function, we then substitute the values, which is the jeq is equal to 0.222 plus 0.022 equal to 0.244 kg meter square. And then we have the BEQ, which is equal to 0.003 plus 0.0005, and we get the value is 0.0035 Newton meter square per radian. Once we substitute, we now have the plan, which is the equation for the plan is GS equal to 1.28 over bracket 0.121S plus 11.2 times with bracket 0.244S plus 0.0035 and plus with 1.6. Once we have the plan, we simplify the denominator to get 1.28 over 0.0295 s square plus 2.0332s plus 1.6392. And now for the PID tuning. For the PID tuning, we use Ziegler-Nichols method to find our value for P, PI, and PID. So in this table, for P we have 0.5 Ku, PI we have the value for Kp 0.45 Ku, and Ti is Tu over 1.2, and for PID the Kp is 0.6 Ku, the Ti is Tu over 2, and the Td is Tu over 8. So to find the real value, to find the value for each of the Kp, Ti, and Td, we substitute Ku to 20 and Tu to 0.5, and then we have new tables which the controller P have the value Kp is 10, Pi have Kp, value of Kp is 9, Ti 0.4167, and since we have the value for Ti, we can find the value for Ki of the controller Pi, which is Ki is equal to Kp over Ti. So we have 21.6, and the controller for PID, the Kp value is 12, the Ti value is 0.25, the Td value is 0.0625. This is all we get all this value from substituting the Ku and Tu on the table above. And for the Ki of controller PID is equal to Kp over Ti, so we get 48 by substituting Kp, 12, and Ti 0.25. And finally is the value for Kp for the PID controller, which is the value for Kp is equal to Kp times with Td. I'm sorry, it's the value of Kd. So Kd is equal to Kp times with Td. So Kp we have 12 and Td we have 0.0625. Time both of these, multiply both of these, we get 0.75. So that is all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and hi, my name is Muhammad Anam bin Abdul Samad. Now I'm going to demonstrate to you how we implement our group project in MATLAB Simulink. So basically, the first one, I will show you how we execute open loop system in MATLAB Simulink. So this is for this system, we use 4 type of block, which is the first one is step block. So in step block, we need to plug in our input, which is our desired value, either 900 rotational per meter or 1500 rotational per meter. But in MATLAB Simulink, we need to convert from RPM to radian per second. So as you can see here, the value of 157.08 is the value of 1500 RPM after we convert it to radian per second. And then for the second block, we use transfer function block. So in transfer function block, we need two type of coefficient, which is the numerator and also the denominator. So the numerator and denominator value here, we can get it after we calculate by using DC-moto equation. Okay, and then the third block we use marks. So marks is a signal editor. So whenever we have more than one signal and we want to show it in one graph, so we use marks. And then this is our output. We use scope block and it can show our graph. So we run the simulation and then this is our output. As you can see here, the yellow one is our desired value and also the blue one is our expected. No, the yellow one is our expected value and the blue one is our actual value. As you can see, there is a gap, which is it cannot reach 100% same as the expected value. Okay, now I will continue my demonstration by demonstrate how we apply PID by tune it manually. So to apply it and tune it manually, we need to use gain block. So as you can see here, we have KI, KP, and KD. So before apply KI by using gain block, we need to apply integrator block, and then we apply KI and input. We compute as 20, and also KP proportional 8, and also to apply derivative block. And the value of KD is 0.5, and then we use sum block to sum 3 of the gain and also plug it into the plant. And also same goes to the previous one, we use marks and scope block to display the output. So we run the simulation and we can see here the yellow one is our expected value and the blue one is our manually tuned PID. So we have an overshoot here. We have an overshoot here, so it not we can say this is overshoot and not 100% give the expected value. Okay, now I'm going to demonstrate to you how we apply PID control by using PID controller. We tune it by using PID controller. So as you can see here, this is our previous manual tune, and this is, we can say it as autonomous PID control. So we use PID controller block. So the first one, the orange one, you can see that this is P controller. So we plug in 10 as the value, and PI controller, we plug in 6 and 15 as the value, and also PID controller, the purple one, we apply 8, 20, and 0.5. So we put it in a same graph so we can compare it. So we will have 5 output of graph. So when we run the program and simulation, we can get this type of graph. So you can see there is 5 color which represent 5 different output. So the orange one is proportional P controller, and the yellow one, same goes as previous, is our expected value, which is comes from input directly. And you can see the blue one is PID control manually. The green one is PI controller, and the purple one is PID controller. So as you can see here, whenever we use PI, PID, and also manual tune, we can get nearly same graph and have overshoot that near to our expected value.
My name is Muhammad Zaizwan Zulhairi. My number is DE220104, and now I will explain about the achievement. For the first is open load system with 900 and 1500 RPM. So let's start with the open load system. at both 900 rpm and 1500 rpm, we observe that the system constantly failed to reach the target output. For 900 rpm, with an input between 95 and 97 units, the output settled around 75 to 76 units. At 1500 rpm, using a 157 unit input, it only reached about 120 to 130 units. So there was no overshoot, but the system responded very slowly with long rise and settling times. So the core issue here is the lack of feedback. Without it, the system cannot detect or correct steady state error. So the second is we do the manual PID control for 900 rpm. To address this, we applied a manual twin PID controller at 900 rpm using gains Kp is equal to 8, Ki equal to 20 and Kd equal to 0.5. So the result show a big improvement. The output now reach the desired value, which is 95.2 units with 0 steady state error. The system also respond faster, settling time within about 3 to 4 seconds. However, we did notice a significant overshoot peaking between 110 and 150 units. This overshoot is beyond the 10% limit set by the project. So while accuracy improved, the transient response still need the tuning. And then the control strategy comparison for 1500 rpm. Next, we compare P, PI and PID control methods at 1500 rpm with an input of 157 units. With P control, the system responds a bit faster than open loop, but steady state error remained. The output settled around 140 to 155 units. PI control fixed this by reaching the full of 157 unit. There was a slight overshoot, about 165 to 170 units. PID control gives us the fastest response and perfect accuracy with no steady state error. However, it also caused the most overshoot, going up to 190 to 200 units and introduced more oscillation, increasing setting time. And lastly, from all this, we can see that PID control gives the best speed accuracy, but only when it's tuned correctly. If not, it can cause instability like servo overshoot or oscillation. PI control offer a good middle ground, eliminating steady state error with less risk of instability. So careful tuning is critical, especially when the system needs to meet both accuracy and stability requirements. That's all from me. Thank you.
This project focuses on how understanding system dynamic help us predict and manage system behavior, particularly through two key parameters, which is the damping ratio and natural frequency. This defines how a system responds to changes, telling us whether it will oscillate, how quickly it settles, and whether it remains stable. Depending on the value of zeta, system can exhibit different types of damping, which is underdamped, where then zeta is less than 1, where the system oscillates but settle quickly. Critically damped, where zeta is equal to 1, system offer the fastest non-oscillatory response. Over them, where zeta is more than 1, where the system settles slowly but smoothly. Undamped, where zeta is equal to 0, where system oscillate indefinitely. When we move to more complex or higher order systems, such as those with third order transfer functions, we encounter more intricate dynamics due to additional poles and zeros. This demand deeper analysis and more advanced tuning methods to ensure control accuracy. This brings us to the broader impact of control theory. It's not just a set of equations, it's a powerful framework that enables smart, adaptive technologies in real world applications, whether it is autonomous vehicles, spacecraft, industrial automation, or smart devices. Understanding these principles lets engineers turn static systems into responsive and intelligent one. By mastering this dynamic, we build systems that aren't just functional, they are also transformative. That's all from us. Thank you.